Okay, we'll continue our discussion of adjustment factors. As we have mentioned previously in our introduction, this is the applicability of our adjustment factor. So given a reference design value, say FV, we have to apply adjustment factor CD, CM, CT, and then CI. So in this video, we're going to go over one by one these adjustment factors. First, our we have the load duration factor. Okay, we know that wood is susceptible to creep due to moisture loss. Therefore, it will follow that the longer a load acts on a wood member, the lower the strength of the wood member. And conversely, the shorter the load duration, the stronger the wood member. So we would have to expect that if we have a type of load that has a very long duration, say the dead load, it is applied permanently, then we have to decrease the strength of the member. And as you can observe here, the load duration factor is zero point 0.9, which means it actually decreases the length of the member. On the other hand, on the other extreme side, we have here an impact load, which has a load duration of about 1 second or less. Then the load duration factor is actually 2, which means you increase the strength of the member because moisture will not have an influence for that very short load duration. Okay? We have to note as well that the governing CD corresponds to the short duration load in the load combination. What does that mean? Remember that we are not just dealing with a pure type of load. Most often, we will be dealing with combinations. Say you have a load combination of D plus L or dead load plus floor live load, then the higher CD or those that are corresponding to the short duration would be used as the CD for that member. And if that is D plus L, indeed you have a CD of 1.0. Let's say you have a load combination of D plus W. What would be your load duration factor? That would have to be 1.33. Okay, that would govern over the 0.9 for dead load. Next is the size factor, and we will divide it into two for dimension lumber and then for timber. So for now, I will have to say that as the depth of wood increases, the strength is reduced, but we will understand it in the next chapter. Okay, so you can notice here that when the size is smaller, say you have a thickness of 4 inches by 5 inches depth, then you have a size factor of 1.4. That is for bending stress. So it varies if it is bending stress, tensile, or compression, as well as the type of grade. So if it is a select structural, number 1 and better, and so on, indeed your CF for FB is 1.4. And as the section uh, goes larger, then the CF decreases. For timber, when the depth D of a beam, stringer, post, or timber exceeds 12 inches, then the tabulated reference design value FB shall be multiplied by CF equals 12 over D to the 1 over 9. Please use the exact dimension, not the nominal dimension. And when beams and stringers are subjected to loads applied to the wide face, then we will use this table instead. So when do we use beams and stringers that in such a way that the loads are applied to the wide face? Can you think of one? So the most common example is the use of stairs, right? As you can imagine, the beam is oriented in its weak axis, and then you step on the member, and so the load is applied to the wide face. If that is the case, and if it is a beams and stringers under timber, then you have to use this factor here. Next is the moisture factor, and we can classify wood based on moisture. If it is freshly cut, then it is a green lumber, or specifically the moisture content is around 30% to 200%. If it is dry or seasoned, on the other hand, then it has a moisture content of less than or equal to 19%. The higher, in general, the higher the moisture content, the more it is susceptible to creep or decay, and then that means lower strength. So if you want to optimize the strength of your member, you have to uh, let it undergo a process of drying. And the wood strength properties peak at around 10 to 15% moisture. As I've said, we can dry our member, and the ways are air drying and then kiln drying to achieve a moisture content of less than or equal to 19%. And if that is the case, then our moisture factor for sawn lumber will be 1.0. If on the other hand, the moisture content is greater than 19%, then we have to use this table instead. Please note the footnotes for FB and also for FC. So if FB times CF is less than or equal to 1150 psi, then we have to use CM equals 1.0. Otherwise, use CM equals 0.85. And check also the footnote for FC. Okay. Next, temperature factor. So as temperature rises beyond 38 degrees Celsius, the strength of wood decreases. But it depends on the moisture condition, wet or dry. That would be based on the moisture content. If it is less than or equal to 19%, then that is dry, otherwise wet. So depending on the moisture condition and then the temperature, we have our temperature factor. Next is the repetitive member factor. Before I explain the provisions, kindly look at this side here. This is an example of a repetitive member. If indeed we conclude that the member is repetitive, then CR equals 1.15. Otherwise, UCR equals 1. So how can we know? When does it qualify? When does a member qualify as a repetitive member factor? You have to satisfy all of these provisions here. Number one, the member should be dimension lumber, and at least 3 members are not spaced more than 24 inches, and then the members are used as joists, truss cords, rafters, studs, or similar members, and then joined by floor, roof, or wall sheathing. Now, what's the logic behind repetitive member factor? Why do we increase the strength if indeed it is repetitive? So the logic behind this is, given that, let's say a member is affected and one member here fails, then the loads can easily be distributed to the other members, to the other nearby members. That's why it is also essential that the members are joined by floor. Otherwise, the loads will not be distributed. So again, all of these provisions should be satisfied before we can conclude that, or before we can use a repetitive member factor CR equals 1.15. Next is the flat use factor. I've kinda mentioned it a while ago in the use of wide face. However, this one is applicable only to dimension lumber. So if the load is applied to the wide face, or it bends about the weak axis, then we can use the flat use factor. Otherwise, if the beam is used as ordinarily as it is, which is about the strong axis, then we have CFU equals 1, or that means the adjustment factor is not applicable. So when it is actually applicable, then we increase the strength of the member. Okay? Again, it has to be bending about the weak axis. Next is the incision factor. This is done when lumber does not readily absorb treatment preservative. And you have to satisfy all of these provisions. Okay? Incision does not actually strengthen the member, but actually preserves the member. So if you won't satisfy these provisions, then we cannot use the member. Okay? So CI will be according to this table. Next is the bearing area factor. It accounts for the increase in allowable stress at interior supports. Applicability conditions: length of bearing along the grain is less than 6 inches and bearing supports not nearer than 3 inches. Before you actually dive into the configurations, make sure first that the support is actually an interior support. Otherwise, this is not applicable. Okay? Then the last two will just be mentioned here. Beam stability factor. It is used to prevent buckling of the compression edge of beam. But this deserves a whole new chapter. This will be discussed in the next chapter, as well as the column stability factor, which will be discussed when we go on to combined forces. Then I have to mention modulus of elasticity, E and E min. The reference design from the table is E and used in calculating deflection, while the reduced modulus of elasticity is used in determining stability factors. It is derived by applying 1 over 1.66 factor to E. Okay?